on the recommendations of their committee, and this is a very big deal because it represents the how we're going to use the majority of observing time on a NASA flagship mission. So for today, I have a very brief introduction for myself on Roman mission status, and then we'll move into the main event, which will be the report from the ROTAC chairs themselves. And I suppose I should introduce them. The ROTAC chairs are Gail Zarowski and Surab Yah. Okay, so let me share my slides, and I will try and get out of the way quickly because nobody really wants to listen to me. But I wanted to briefly have the floor so that it's clear that everybody understands that Roman is real. It actually exists. You're looking at it right now. Can everybody mute, please? What you're looking at is the main part of the observatory. So at the moment that I took this photograph, which was taken last Monday, they were lifting the cover off the mirror. That's the white cloth thing being lifted up by a crane, and that's because we're preparing SCIPA, the spacecraft was integrated payload assembly, for vibe testing. In the foreground are the flight solar panels, and there's one more piece of the observatory, the bit that will surround the telescope and the deployable aperture cover, and that is completing testing in the SES chamber. So for where things stand at the moment, we have 100% of our flight hardware. Everything has been through environmental test, and that means that every part of Roman hardware has been through the most extreme conditions that we will experience. The observatory is in two large pieces, each of which are going to continue through testing in parallel, and then will be assembled this autumn, complete final testing, and be ready to ship to Cape Canaveral in July, or possibly June if we don't get the observatory meets or exceeds all science requirements, and this has been important for the design of the surveys, and we're on track for an early launch in October 2026. And I want to highlight that we've been planning for a launch in October 2026 for many years, but this is in fact 7 months early, that our launch commitment and what we're budgeted for is for a launch of May 2027. You're going to hear today the outcome of the community process to define our 3 core community surveys. And I want to take a brief moment to mention the path that we took to get to the point of starting the community process. So following the top recommendation in the 2010 decadal survey, a science definition team was convened and produced a report in August 2012 that outlined some options for mission designs, all of which included mirrors of the roughly, just over a meter scale. And at that point, the core surveys included all the ones that we're currently familiar with: a high latitude imaging and spectroscopic survey, a time domains, high latitude time domain survey, and a galactic bulge time domain survey. It also had a galactic plane survey as one of the core surveys. By this, a second science definition team produced a report in May 2013 because this represented the transition to a 2.4 meter primary mirror. There were significantly more detailed survey designs. The field of view had got smaller, the science of the mission had changed. It dropped the galactic plane survey, but it did include a detailed review of over 50 possible General Astrophysics Survey programs. So this was a clear effort to broaden the science reach of the observatory. The third report was in March 2015. This included more detailed consideration of astrophysics from the core surveys. It assumed a geosynchronous orbit. In 2016, we solicited proposals for a set of science investigation teams who formed the Formulation Science Working Group. The observatory is now back to an L2 orbit. This is the group that developed the design reference mission that we carried through for our system requirements review, for our preliminary design review, and our critical design review to verify that the observatory that we were designing really could meet its science requirements. This is also the group that introduced the concept of community definition of the core surveys and started those discussions. Between 2021 and 2022, the Roman Science Interest Group helped us flesh out the concept of a community definition process. The Committee for Astronomy and Astrophysics, which is a National Academy committee, reviewed our plans for developing the Roman Observing Plan. And then finally, we added the Galactic Plane Survey as an early definition General Astrophysics Survey. So there's, over a decade of work on Roman and Roman observations prior to the formal start of the community process. And I think the reason that we were able to get design such a great plan is because all the work that had gone before provided the infrastructure that allowed us to quickly evaluate the return from the updated designs. I wanted to comment a little bit on what I feel that we've achieved with the community process. I think it has been spectacular in broadening the science input for each survey. And by that, I mean not just the breadth of science cases that are reflective of where the community and where science knowledge is right now. It also broadened the number of voices, the number of institutions, the number of countries in the world, which was really fantastic. The survey recommendations all include optimizations for astrophysics, which is extremely important because astrophysics is our top mission objective. The considered synergies with other facilities. Roman doesn't operate in a vacuum, and it's important to make sure that we take advantage of all of the other capabilities that are around in designing Roman surveys. There's many people who've been involved and contributed to this process. Leading up to the community process and during the community process itself. And everybody who's contributed has been important. And this is extended from people who wrote pitches and white papers and produced presentations for the various workshops, who did simulations and analysis, who served on committees, who supported committees, and much more. You'll hear about the final report in the talk that follows mine. I wanted to say here that I think I've read the report and I think it's excellent. The project plans to accept the recommendations in the report, and the implementation, the precise implementation, will depend on implementability and precisely when we launch. But we expect that the surveys that we conduct will be what you see in the report itself. And that's all that I have. So I will stop and let you get to the actual important part of this meeting and invite Saurabh and Gail to tell us all about it.
right. I apologize. I'm not used to using WebEx. All right, thank you, Julie. So I'm going to open and then I'll trade off with Sarab as we go. So this is the report and our final recommendations from the Roman Observations Time Allocation Committee. We wanted to start just going off a little bit more detail off of the very end of the timeline that Julie presented. As she emphasized, this is the culmination of literally decades of work by many people. What we're going to talk about today is some of the specifics that have come out of the very last steps of that. So her timeline ended in 2022, 2023. What we're going to present today was based heavily on white papers that were solicited from the community. 2023, 2024 saw the sort of the coalescence of these core community surveys and what form they were going to take over the next several years. So we wanted to define a couple of acronyms here because we're going to be using a lot of those throughout these slides. So core community survey. So you see CCS, these are one of these three core community surveys that we'll be talking about. Each of these was helmed by had assigned a definition committee, which was charged with taking all of the science input from the white papers, from the science pitches, from all of the various other teams that have formed to look at some of the technical issues and constructing survey options. And I'll go into that in a bit more detail for each of these core community surveys. There's three core community surveys, the Galactic Bulge Time Domain Survey, the GBTDS, the High Latitude Time Domain Survey, HLTDS, and the High Latitude Wide Area Survey, HLWAS. And I will spare you how I pronounce those acronyms in my head. But we're going to go through our recommendations for each of those in order. So the ROTAC itself, the Roman Observations Time Allocation Committee, was convened last November. In January, all of the reports from the core community survey definition committees were released, along with presentations explaining the highlights. And you can find these slides will be made available, and you can find those reports and those presentation recordings at those links. It is now April 2025, so we are doing our report and presentation now. One of the next major milestones that we're super excited about is next June or August. Sometime in northern summer will be the first General Astrophysics Surveys programs will be selected. I believe the proposals will be due earlier that year. And then those first programs will be announced. And then I guess the next big milestone currently is looking at September, October launch, this big purple triangle here. Okay, just also to reiterate what Julie had said, this really was a community-driven process that definitely preceded my participation in this. So here we're showing some maps of the institutions of individuals who provided input into this process just over the last couple of years. So this does not include people who have been working on this for the last 20 years, but this is the institutions of everyone who has who contributed white papers, who proposed science pitches, who served on the project infrastructure teams, on these definition committees, or on the ROTAC. So really spanning 6 continents, which I think really demonstrates the level of enthusiasm we have around the world for this very, very exciting project. Just to say about the membership of the ROTAC. So I'll just read, I won't read everyone's name here, but you can see that this spans people who span a wide range of participation and a wide range of scientific expertise. And then we had several ex officio members from the project itself who were invaluable for helping us understand some of the more technical definitions and technical issues of the project. Okay, so the charge of the ROTAC was to review the survey design options from each of the definition committees. So here I'm showing a table of numbers. On the left-hand side, we see if every definition committee was charged with coming up with a nominal survey given some time allocation, and then an underguide and an overguide, with the differences of about 20 days for each. These were the surveys that we were presented with. We were asked to choose amongst these, essentially. I mean, all of the hard work was really done by the definition committees in designing these surveys to maximize different aspects of the astrophysics. We were asked to choose amongst these, keeping in mind the balance between these community-defined surveys and the general astrophysics surveys, which will be defined in a more PI-led kind of way, in goal of trying to maximize the total science across all of the observations. Just a note, this does not include any of the coronagraph observations. We were only looking at the wide field instrument observations. Yeah, so I guess giving away. So our first recommendation, the total number of days, so we're looking at about 3/4 of the time, a little bit, just under 3/4 of the time to these community-led surveys, and then just over 1/4 of the time for the General Astrophysics Surveys. And then to put a little bit more detail on that, so we are recommending the nominal design plan, the in-guide survey option, 520 days of observing time for the high latitude wide area survey, the in-guide observing time, 180 days for the high latitude time domain survey, the over-guide allocation, just under the 440 days that was shown earlier, so 438 days for the galactic bulge time domain survey, with a couple modifications from what is outlined in the definition committee report. And that leaves 389 days reserved for the General Astrophysics Surveys, which is, again, just over 1/4 of the time of the prime mission science operations time. And this includes the early definition galactic plane survey, which we'll say a little bit about going forward. So, Sab.
Great, thanks, Gil. So here you see the sky map for these surveys, including the galactic plane survey. So maybe I'll go in order of increasing area. So the smallest area is covered by the galactic bulge time domain survey. That's the one we recommended, the overguide option. So that's that yellow circle right in the middle, right near the galactic center. So it spans, and you can zoom in, you can see on the lower right there. So it spans 6 fields, one of them which is the galactic center itself, and so I'll talk about that survey in just a bit. Then the other kind of sort of small survey in terms of sky area is the high latitude time domain survey, and so that has 3 regions on this map in blue. There's a northern field, and we'll talk about there's 2 tiers in each of these, the northern and the southern field, and then you can see the southern field is the Euclid deep field south field. There the deep tier and the wide tier, which I'll mention in just a second, are slightly separated on the sky. And then moving up for the core community surveys, there's the high latitude wide area survey, which is the largest on sky. It also has tiers, deep tier, a medium tier, and a wide tier, and you can see those in green. There's also a process going on to define this early definition galactic plane survey that's still under development, but we think it's basically going to look something like this, cover the inner part of the galactic plane, more of the bulge than the galactic bulge time domain survey. So this is a pretty representative view of what the sky footprint of the galactic plane survey will look like. Okay, next slide, please. Okay, so one of the important issues that we wanted to make sure is that all of these surveys as proposed, they were sort of proposed in isolation, could be merged together in a coherent plan, in a coherent observing timeline. So thanks to the work of the mission simulators at the Science Operations Center at Space Telescope, we can say, yes, it looks like it can be planned. And so you can see kind of the rough outline here. The galactic bulge time domain survey looks at the galactic bulge in these bulge seasons, and it sort of fills up those seasons, and they would like 3 of those seasons early in the survey that you see there in the yellow on the left, and then 3 later on in the survey. The high latitude time domain survey, its main component is in the middle, all those picket fence stripes that you see in the middle 2 years. That's when its core component is going, but there is an early part, a pilot survey, and then there are extended observations later on in blue that you see there. And then the wide area survey is not so dependent on the cadence or the time of observations, and so it sort of fills in a bit of the gap. And then you can see the galactic plane survey, which also needs to survey the bulge, and so it's hard for it to get time while the bulge survey is going at high cadence, and so you can see it comes in at sort of the 4th bulge season is when the galactic plane survey gets scheduled in the simulation. There's a tiny bit of time in the galactic plane survey in that first season. You can see that spike there. So the really nice thing about this is that, you know, it seems like it works. You can fit in these surveys into a good plan. There are a few spikes that you see here that go above 1. 1 is the total amount of resources you have. So going above 1 is not good. But actually, these are pretty well understood to be artifacts, and the team is pretty confident that they can work around these. The white space that you see is time for other surveys. So for in particular, the General Astrophysics Surveys. And one of the important ideas is that there is time for that throughout the 5-year prime mission. Thanks, Gil. Next slide, please. We're going to talk about filters a bit. So just a reminder of what the Roman wide field instrument filters, the imaging and spectroscopy capabilities are, the wavelength coverage. So they're the Roman filter names, F062, F087, and so on. There's the shorthand filter names. There was an R which disappeared somewhere for F062, but then ZYJHWK. The F is the F184 filter. That one, F146 is quite a wide filter. You can see it better in the right-hand panel. And then you can also see the wavelength coverage of the prism and GRISM spectroscopic elements. Okay, next slide, please. All right, so let's start with the galactic bulge time domain survey here. This is where we recommended the overguide option. So this is what the plan looks like. There are 4 parts of it. So it's going to observe these 6 fields near the galactic center. So 5 of the galactic bulge fields you see just to the south of the galactic center and the galactic center itself. And then it's going to have 6 of those high cadence seasons, those yellow blocks that you saw in the timeline. So the first and last, whatever the last means, 3 bulge seasons. The cadence is 12 minutes, and we'll talk about that in a second. There was a lot of astrophysics that was enabled by going to a faster cadence. And so going to a faster cadence for the galactic bulge time domain survey, and then with the exposure time that you want, leads to these 5 fields for the main science plus the galactic center. Okay, so you get about 67 seconds exposure time. These observations are all done in the wide F146 filter, the W filter, as sometimes it's called. Okay. And then every so often, so maybe every 12 hours, this is still TBD, and exactly which filters is also TBD. These fields will get observed in the Y band F08, the Z band F087, and the K band F213. Okay. In addition to the high cadence seasons, which is the majority of the observations, there are 4 low cadence seasons. I'll show you that in just a second. We have some constraints on when those get observed. I can talk about that. And then there's also 30 photometric snapshots and 5 filters to cover more filters, and then 30 spectroscopic GRISM snapshots of these 6 fields. Next slide, please, Gil. Okay, so this is what it looks like in time. We saw those high cadence seasons. That's when those fields will be observed for about 70.5 days with 12-minute cadence just going, bang, 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 bang on all the fields and just repeating that every 12 minutes for 70 days-ish. And then, so those are those 6 seasons in red that you see. Then there's also the low cadence seasons, and those are important just for what this plot illustrates. This is from one of the white papers, that there may be some long time scale microlensing events, which are not exoplanets, but in fact, this would be a free floating black hole, making this several year long duration microlensing event. And you would like to catch those too. You wouldn't want to miss it just because the survey wasn't observing the bulge at that time. And so obviously with this kind of time scale, a low cadence is fine to cover this light curve. And so this is the idea of the low cadence season. And you can see the breakdown there. The high cadence really takes up the bulk of the time. The low cadence observations is just a little bit, but it adds a lot of extra science like this. And then the snapshots, I'll talk about the science there, that just happens regularly throughout all the bulge observing seasons. Next slide, please. Okay, so what is the science? So the high cadence seasons, that's really for the main science driver. The level 1 requirement for Roman is to conduct a census of exoplanet demographics via microlensing, and particularly looking for small planets, low mass planets far out that are not well probed by other exoplanet detection techniques. So that was the real design goal for that, and so things are sort of optimized for that science case. But the high cadence seasons also have a lot of other science, the transiting exoplanets, astroseismology. The galactic center is not actually the ideal place for the microlensing, but it has lots of ancillary science. I encourage you to look at the definition committee report about all the great science you can do at the galactic center. That was just a key thing that just made sense to include as part of this survey for sure. Excellent science there. The low cadence seasons, I mentioned, black hole microlensing, more massive object microlensing, long period variables towards the galactic center, etc. The snapshots will give colors and extinctions for all the stars, that you can get the multi-band coverage to get that. And then the GRISMs can also get you spectra of the brighter stars, and you can even do kinematics, you can do radial velocities, and then you can also identify binary stars as with those 30 GRISM snapshots over the 5 years. All right. Next slide, please. Okay, so we also, of course, consider the underguide and nominal for the galactic bulge time domain survey. The underguide removed, in all the cases, the underguide was sort of what you needed to just barely be sufficient to meet the mission science requirements. Okay, so the underguide really focused on the level 1 science requirements. In this case, it would be the exoplanet microlensing, and you would lose a lot of the other science by doing the underguide. So in this case, no high cadence observations of the galactic center, right? Because that's not the focus is not the exoplanet microlensing for those. No low cadence seasons and minimal snapshot observations. So the ROTAC really thought that this was losing a lot of important science, and so we didn't recommend the underguide here. In the nominal, the plan would be to do a slightly slower cadence, 15 minutes instead of 12 minutes, and then you'd have less time in the low cadence seasons and less of the snapshots. The ROTAC was really convinced that the faster cadence, 12 minutes, was quite important, especially, for example, for the small radius transiting exoplanet case. So things like that kind of science really pushes you towards faster cadence. The exoplanet microlensing is somewhat ambivalent between the two, but the extra science you got from the faster cadence and the fact that like once you choose a cadence, you lose all information faster than that cadence, really pushed us to want to go to the fastest cadence that still got you a reasonable sky coverage. And so with the overguide, you're able to do this 12-minute cadence, but again, that 12-minute cadence means that you have to do a slightly less sky area. And so also the overguide extended the seasons as much as possible so you could make up for that loss in sky area. So this kind of speaks to how the ROTAC approached this kind of thing. So it's, in many cases, the overguide or nominal decision was, not just the level 1 science requirements, the core science, but these ancillary science. And we sort of, the way we thought about that ancillary science was like, if it made sense where it would really be impossible to do that science as a general astrophysics survey. For example, the galactic center observations, like they would be right where the bulge is pointing. So if the bulge time domain survey happened without those, it would be really difficult to propose for that galactic center observations just because of the scheduling issues that posed. So it just made sense to include that as part of the survey. And that's kind of the lens we used for some of the decisions, is to, like, when did it make sense that this really should be part of the core survey, or no, this could be something that's proposed for and competed in the general astrophysics pool. And in this case, we really were convinced that the extra science you got from the overguide really was a worthwhile investment of sort of 20 extra days of time. In fact, it was actually 18. We'll get back to that in a second. Okay, moving on to the high latitude time domain survey. So here the structure again is 3 kind of parts. There's the core survey, which you saw that picket fence in the center 2 years. There's the extended high latitude time domain survey, getting observations before and after, and then there's a pilot survey early on. And I'll talk about the rationale for all 3 of those. And then this was here, we recommended the nominal allocation of 180 days. Next slide, please. Okay, so the main science goal for the high latitude time domain survey is to do cosmology, measure the expansion history of the universe, constrain the nature of dark energy through observations of type 1a supernovae. So discovery and follow-up of high redshift type 1a supernovae. And so that was the main focus that drove the survey design parameters. And the strategy that was adopted was to have 2 tiers. One is a wide tier, which focuses on type 1a supernovae around a redshift 0.9. So that was sort of the design redshift, but you can see that it actually covers pretty broad range there that you see in blue. And then there was another higher redshift tier, the deep tier, that looks at type 1a supernovae redshift 1.7. And here really Roman is sort of the only thing that is uniquely capable of finding and observing well type 1a supernovae at those high redshifts. And so the definition committee really looked at what were the unique strengths of Roman, and focused their design, their survey design on leveraging those strengths. Okay, so in the survey, in the wide and deep tiers, they basically have overlapping filter sets except for one. Since the deeper tier is going for higher redshift, the filters shift over to the red by 1. There's a 10-day interlaced cadence. In the wide tier, you get R every 5 days, and then you get Z and J or Y and H every 10 days. And then similarly with the deep survey, you get Z every 10 days, and then every 5 days, excuse me, and then YH or JF every 10 days. There's also, that's about 80% of this core component. About 20% is prism spectroscopy. I'll show you what that looks like for these supernovae in just a bit. There's a pilot component, and so that you get all the fields early on. There are a few reasons for that. One is just to get templates. You'd rather not have templates while the supernovae are alive. So having some templates early from a year before the core survey, those will be clean survey templates. The supernovae, the type 1a supernovae will be gone in those, and then you can find fresh supernovae as soon as you start observing in the core component. There's also some other things like the type 1a supernova rate at high redshift is uncertain, and so the pilot observations will better constrain that and let people know whether modifications to the core component might be necessary. Then there's also an extended component that's basically looking at time variation over longer time scales. So we'll see high redshift exotic transients, which have very long time scales. But this will be great for all kinds of extragalactic transients, not just type 1a supernovae, supernovae all types, AGN, all sorts of extragalactic transients will be really well probed by this survey. As I mentioned, there are two fields. One is the Elias North field, and you can sort of see that the deep and the wide are sort of contiguous in that field, whereas in the Euclid Deep Field South, the deep and the wide, one of the circles, I forget which one is which, one of the circles is the wide area, the other circle is the deep area. This just matches the Euclid footprint for this field, and also the Rubin deep drilling field located at this position. Next slide, please. Okay, so these are some examples of what the light curves look like. So in the middle two panels there, you can see from the deep and wide surveys, as you increase redshift, what the type 1a supernova light curves are doing. And then on the left-hand side, in the beautiful rainbow plots, you can see the redshift distribution of the type 1a supernovae up to some signal-to-noise ratio, some cumulative signal-to-noise. So the higher the signal-to-noise, the better sampled the light curves are. But then, of course, those are the brighter objects at lower redshift. And then if you go sort of, ideally, you would want the cumulative signal-to-noise of somewhere around 20, 30. Those are the green. And so in green, you can kind of see what the expected distribution of the type 1a supernovae that are going to be used for cosmology from Roman will be. And if you squint, you'll see the numbers there are, 6,000-7,000 supernovae in the deep tier, similar numbers, a little bit more in the wide tier. So talking about something like 14,000-15,000 type 1a supernovae, well measured for cosmology, coming from this kind of Roman survey design. And by the way, I should mention this is from a paper led by one of the proposal infrastructure teams, led by David Rubin, presenting, doing these simulations for these supernovae. Next slide. That was the imaging. Here you can see what the spectra look like with the prism. And again, on the left, you can see kind of the cumulative signal noise for the spectra, what the redshift distribution of objects with spectra would look like. And, the amazing thing for Roman is we're pushing to redshifts above 1 that are largely unexplored, can't really be done from the ground, can't be done in large numbers from any other kind of facility. Even Rubin is going to struggle much above redshift 1. And so Roman is going to, really do amazing supernova science at these, redshifts like 1.5, et cetera. All right, next slide, please. Okay, so for the highlighted time domain survey, we went with the nominal allocation. The underguide eliminated the extended component, so that lost a lot of interesting science, like this high redshift transient science, and it reduced the imaging area, so that reduces supernova numbers, and that didn't seem like a good idea. So the ROTAC was not in favor of that. The overguide, the emphasis was more on community science, so adding filters, adding a deep K-band observations, et cetera. And here, the science was certainly good, but the scheduling, the cadence of this did not, it did not scream out that this needed to be scheduled, at the same time that the rest of the survey was being scheduled. And so this seemed like a perfect idea for a case for, this is something that really should be competed in like a General Astrophysics Survey proposal, and then it can kind of build on the nominal core community survey if that ranks well against other ideas that people might have. And so because it didn't seem like essential to include it with the survey, we didn't favor the overguide option in this case. Okay, I think Gail, you're taking over now.
Yeah, so the high latitude wide area survey, so I'm going to start with the science here. So the main goal here is cosmology, is understanding the growth of structure, understanding the cosmic expansion of the universe across cosmic time. And so approaching it using imaging and spectroscopy. Imaging, the main goal is to do weak gravitational lensing. Spectroscopy, the main goal is to get galaxy clustering to measure baryon acoustic oscillations across time, and then also redshift space distortions. Because this is a large area imaging survey, also a huge range of applications for general astrophysics. So everything from galaxy and black hole evolution across redshifts, even to resolved stellar populations, galactic structure, all the way down to solar system science. So the recommendation, so we are recommending the nominal in-guide allocation for the high latitude wide area survey. This is built around a three and a half tier kind of structure. So the medium tiers, this is 2,400 square degree 3-band patch of sky with both imaging and GRISM spectroscopy. This is sort of the central workhorse of the survey, I would say. It allows detailed calibration of your weak lensing measurements and just serves as a general purpose wide area redshift survey. So this is where a lot of the general astrophysics can come from. So this is really a new regime for Hubble resolution near infrared imaging. And think Milky Way stellar populations, local galaxies, galaxy halo studies over a huge range of redshift. The wide tier is 2,700 degrees squared. I should emphasize this is 2,700 square degrees on top of the medium tier. So this is additional. This provides additional imaging area in a single band, so both for cosmology and for general astrophysics. A large number of the white papers and science pitches really advocated for a very, very wide field survey, and so there was a lot of interest in this tier. For example, it more than doubles the statistical power of the weak lensing survey. So this is really going to be transformative. The deep tier, this is about 20 square degrees, just a little bit less. This provides really, really important calibration for the medium and wide tiers. This includes more filters, so a huge number of filters, and GRISM spectra for instance, spectra Zs. This also has a much denser time sampling, and so this will be really valuable for some time domain science applications, including solar system objects even. And this also includes an ultra deep region, which is 5 square degrees with very, very, very deep Y, J, and H imaging. So one way to put this in context, this will reach a similar depth as the NICMOS observations in the Hubble ultra deep field, but over an area that's just under 2,000 times larger. Yeah, so very, very exciting. We put a table in here. I am not going to read these numbers. This is just a breakdown of some of the details of exposure times, depths, and yields for the different tiers. The only thing I really want to point out on here is the 600 million galaxies with shape measurements for the weak lensing survey and 19 million galaxies with spectroscopic redshifts coming out of here. So really just having that 5,000 plus square degrees of area on the sky gets you so much. And again, this is something that Roman, with its enormous footprint and high resolution, is really, really excitingly poised to do. For the underguide and overguide scenarios here, so the underguide option was essentially a reduction of the wide tier area in both the north and south galactic cap regions. The ROTAC felt that this was just too great a loss of area coverage and science return compared to the nominal survey. Again, this is where Roman shines, and so it seemed not like a good idea to not let it shine. And then the overguide option was primarily centered around expanding the wide tier in the southern half of the sky, which maximized overlap with some other data sets. And similarly to the time domain, to the high latitude time domain survey, this was obviously provides some compelling science, but the ROTAC felt that it didn't add a broad enough science impact to merit including it in the core community survey. And so we went with the nominal option for this case. Okay, Saurabh, did you want to do this one?
Sure. By defining these options for the core community surveys, essentially what was left over was our recommendation for the General Astrophysics Surveys. But just because we presented it this way, I just wanted to emphasize, so this left about 389 days for General Astrophysics Surveys, including the Galactic Plane Survey, which takes about 30 of those days. But the ROTAC really emphasized and valued the General Astrophysics Surveys, and we really saw our role as stewards of this highly valuable General Astrophysics Survey time. So we really looked at the core community surveys each on their own merits, knowing that if we had chosen the underguide or nominal option, that would use up or leave free more time for General Astrophysics Surveys. So this thing really was in our mind for a lot of the discussions and our thinking about which options to recommend. So for the General Astrophysics Surveys, there are about 30 of these are envisioned over several proposal calls. And as Gail mentioned, the first one likely in northern spring of 2026. But because there's only 30 and there's sort of 389 days, if you do that division, we sort of anticipate that these general astrophysics surveys should be large. It would be kind of not the best use of Roman if you're going to point this wide field instrument at your favorite little target on the sky. And so I think the success of this community-driven process for the core community surveys really suggests a way that general astrophysics surveys should probably also be done, in that it would be great to, if you have a great proposal idea, talk to other people, get a community together, and use that to make broad science goals to make the best use of the Roman survey speed. So I think this process that we've been going through could be a model for even how PI-led proposals with Roman get done. So we were really positive about that kind of aspect. And in some cases, those observations that are from the general astrophysics surveys could be complementary to or build on, another filter on the same fields of some of the core community surveys. So those could be considered and competed with other ideas. I think that would be, really exciting to see what ideas people come up with. From the timeline on the lower right, you can see that there is room for general astrophysics survey observations throughout the 5-year prime mission. Even early on, you can see, not right at the beginning, as this launch date puts us right, into a high latitude, a galactic bulge time domain season right at the beginning. And so there's going to be very limited time right then, but you can see there is some unused time just after that in that first year. So it is even possible in that first call to get relatively early data with the general astrophysics surveys. So there are some limits, but there is room for general astrophysics observations throughout the 5-year prime mission. And of course, we are quite hopeful that Roman will have an extended mission, beyond the 5 years. And there it is anticipated, though not at all settled, it is anticipated that general astrophysics surveys would comprise a larger fraction of the time in an extended mission. Of course, as we get data, we see the capabilities, that'll really allow us to rethink what general astrophysics surveys with Roman could be.
All right, so just to recap everything that we've said, so the ROTAC recommendations have settled on a balance of roughly 75%, 25% of the wide field instrument observing time for the core community surveys and the general astrophysics survey programs. We felt that this was a good balance that maximizes the total science return across astrophysics spanning from the solar system to cosmology. The observations that were recommended, the observations and the observation cadence that were recommended by the definition committees, we generally recommended those as well because they seem to facilitate all of the baselines and the cadences that were necessary for the time domain science. And all three made compelling cases for why early data was necessary. So all of the core community surveys and the galactic plane survey will be taking data in the very early phases of the mission. We do have, and we go into much more detail in this in the report, I'm not going to go into that here, but there are a couple of cases where we think that there's some extra care that could be taken to increase the efficiency of scheduling the core community survey, both for the core community surveys themselves, but also to maintain some flexibility for the remainder of the general astrophysics survey observations, because we want to make sure that people can not only have time, but sometimes it does matter where in the year you have that time. And then we also recommend that there be mid-mission reviews of the core community survey performance, both from a data perspective and from analysis perspective, but also where that fits in the evolving scientific landscape where we're going to be in the world in a couple of years. Oh, sorry. Nope, I want to say that. Okay, so we wanted just to end on a note. We think the ROTAC committee was really impressed with this community-driven approach to designing the observations of this large mission. We think that it's really going to allow Roman to address the most compelling and exciting questions from exoplanets all the way up through cosmology, while also enabling a huge range of astrophysics along the way. We were so impressed with the cases that came from the white papers, that came from the science pitches, that were consolidated by these definition committees. It's so very exciting. So when we combine these core community surveys with the galactic plane survey and the as yet to be determined general astrophysics survey, all of these data are going to be fully public as soon as they're taken. We think that the science portfolio of this next flagship mission is going to be hugely transformative, obviously much longer than this 5-year prime mission, and absolutely excited. Cannot wait to see where this goes, and I've been delighted to be part of this process. we really want to extend our gratitude to all members of the community who have participated in this, both through all of these things that I keep mentioning over the last couple of years. But as we said at the beginning, this is the culmination of a planning process that started nearly 20 years ago, and a huge number of people have contributed to that, both formally and informally along the way. So thank you to all of you for making this science doable, I guess. In particular, the members of the definition committees for the 3 core community surveys that we've talked about today, and then we also personally the ex officio committee members and other members of the Roman project staff and scientists who have really helped frame our recommendations and understand how these core community surveys play against each other and what the impacts on the general astrophysics surveys are going to be. And just finish with making you look at all of our pretty mugs. So these are the members of the ROTAC. At the bottom are pictures from our in-person meeting at Space Telescope and our visit to Goddard to actually see the telescope under construction. So I think we will end there and take any questions. Thank you.
Thank you. Thank you so much. I can't see if anybody has their hand up. I thought I saw Robin Sanderson, but maybe it went back down again. Anyway, does anyone have questions? Please raise your hand and we'll call on you.
While we're waiting, there's one in the chat about the exposure time for the high latitude time domain survey. So Gail, could you go back a few slides? Because that's on a slide. It's not a number I remember off the top of my head. Yeah, here. So, oh, I guess it's not actually in the imaging exposure times. It's in the report. I believe the report will get is posted already, and a link will get sent around. But it is in the report and in the definition committee report.
Yeah, we tried not to overwhelm with numbers here.
So there's a couple of questions that have come up that maybe I can address. So one of them is are the pixels going to be available after supernova and other transients have been identified? And the answer is yes. We preserve all Roman data. It will be accessible through the Roman Research Nexus if you want to do analysis in place, or you can download it in the normal way. The second question is how much time for General Astrophysics Surveys in the first cycle, and that's TBD because the mission plan depends quite sensitively on when we launch. So a shift by a couple of weeks could put you in a different place on the phasing of the galactic bulge time domain season regions. Our thinking is that there will be proportionally less general astrophysics survey time at the beginning of the mission, so that we preserve more time when the observatory is well understood for proposal-driven and other community-defined general astrophysics surveys.
Thanks, Julie. I actually don't know how to see the chat while I am sharing, so which is why I'm not responding to anything else.
There are a lot of people helping out with the chat, so thank you so much.
Okay, great. Good.
There's a question from John Wu about what are the criteria for a galaxy to have a viable shape measurement in the high latitude wide area survey. I don't know, maybe Ryan, if you're on, or maybe David could speak to that, or Risa.
So I want to make sure I get this exactly right. So David may know off the top of his head, but I'll go look at the report to confirm that.
More questions. It's actually working pretty well to have the questions and answers pop up in the chat, but people should.
That's great. I should be looking at those too.
Questions in the normal way.
Will the chat be preserved as part of the recording? Because I can imagine people watching this later might want to know some of the same things.
I don't know, but we can capture it and post it next to it.
Okay, that'd be great.
There are some hands. So I think
Julie, there was a question from Lynn about what set the 30-day allocation for the galactic plane survey.
So the 30-day allocation, the goal was to provide enough time for a substantive survey, but because we knew we were going to have it be scheduled in the first 2 years, the RSIG felt quite strongly that we wanted to be careful not to allocate too much too early.
Certainly, galactic plane science could be part of General Astrophysics proposals as well, right?
Of course, absolutely.
There's no restriction on what a General Astrophysics proposal could be with the wide field instrument.
Right. Right. I mean, so you probably, in the upcoming general investigator call, if there's, something like, I don't know, 100 successful proposals, about 6 of them might be for new general astrophysics surveys. But, there's lots of science and analysis that needs to be done on, the surveys that are already defined.
Thank you very much for your hard work. So I have a question about the high latitude wide area survey. So now we know we have a deep component and the ultra deep component, and I just saw the report carefully, and there is no mentioning about cadence. Is there any possibility of introducing cadence there? And if that is the case, Transcend team are very much interested in collaborating with that part. Is it still TBD?
I can try to answer that one.
To put Ryan on the spot again, great.
Yeah, sure.
And just to clarify, the reason we're calling on Ryan is because he was on the ROTAC as a representative of the definition committee for the high latitude wide area survey. So we're not just picking on him.
Yeah, so thanks for your question. That is also still TBD. As you saw, the scheduling is kind of complicated. And so the emphasis on cadence for some of the deep field observations was placed more heavily on the high latitude time domain survey, where the level 1 science requirements required the cadence a particular cadence very explicitly. There's one particular bit of cadence in the deep fields that we have included in discussions with the planning team, which has to do with separating some observations in such a way to pick up solar system objects. So there was a great deal of interest in solar system objects, and those fields are fairly, close enough to the ecliptic that you can get really interesting detections potentially. And so there's a criterion in there about the separation of getting 2 observations within, roughly a day, a day to a week, so that you can potentially see moving solar system objects. Any more detailed cadence than that, there were some suggestions in a number of the white papers. Those have been sort of thought about, but given the complexities of scheduling and everything else, those have not been placed in as constraints yet. But I think at this point, I would strongly encourage folks to communicate with us or with the project team if there's additional constraints that may be possible.
Yeah, thank you very much. In March, there was a transient meeting at Space Telescope Institute, and this deep field was not known among transient teams. So it'd be nice if we can collaborate and optimize the cadence. Thank you.
Great.
And one thing, and it's a relatively small area, so it'll be easier to do the cadence constraints on a small area than trying to say, oh, the whole wide area survey has to be observed in a certain way. So I think,
Yes.
that's definitely possible, and everyone wants to hear those ideas. So
Yeah. Just to say, there are also constraints that at least some of the deep area will be done early in the mission, because it's required for calibration of the wider areas. And so so that places, some constraint on cadence as well, but that is an important consideration.
Jashanpreet has his hand up. Do you want to ask your question?
Thank you so much, ma'am, for giving me this chance. I just have one question that I used to do research on AGNs recently, and I have encountered some issues like they are very outshining the galaxy, host galaxy, and we need to process that using the GalFit. So is there any chance that in the upcoming mission, that is Roman Space Telescope, the data will have some ease, that we will be able to process more easily the galaxy part out of the outshine AGN nucleus? Will we have something ease for the imaging part of the telescope?
So I don't know if you're asking about software tools, but one thing that will be definitely different, of course, is with Roman at the spatial resolution, will be something like 0.1 arc seconds compared to the Sloan images on the ground. So the light from that nucleus will be much more confined to the center of the galaxy. So indeed, you should be able to see the host galaxies of many more AGN with the data. Now, I'm not going to say that it's going to be an easy challenge, an easy software challenge to separate the AGN light from the galaxy light, but it should be certainly easier than from the ground.
So actually that's an issue because we already have to shift to the Linux for processing all the data stuff for the AGNs. However, I tried to build my own Python package for the processing of the AGNs, Galamo, but that's what the issue, and we are still facing like GalFit. We need to specify the model stuff for that imaginary part of the telescope. So that was I was expecting that is there any chance of getting a good data. However, James Webb Space Telescope has issued some ease than what we have from the previous telescopes for the agents data. However, I will be very glad to see a good data from Roman telescope. Thank you.
Thanks.
Thanks.
Okay, I think that might be a wrap. So I want to echo everybody else and express huge gratitude to all the members of the ROTAC, and in particular, Gail and Saurabh. It's really hard to imagine how this process could have gone much better. Thank you so much. Josh.
Okay.
Thanks, Julie. I just wanted to also say thanks to everybody out there in the community who participated in this, and to the committee in particular who put this all together. I mean, the report and this presentation were a huge success, and we just want to say thanks. We look forward to all the great stuff we're going to do with this observatory and the wide field instrument.
Absolutely, and I want to point to those of you who are still online. Ori just posted a link to the Roman Science Collaboration link into the chat. So if you haven't signed up for that already, please do so, and let's keep the conversation around this planning going forward.
So just a very quick question, and that is that the Access Community Science online meeting is going on right now, and two of the working groups are meeting today, of which I was taking notes for one of them. Is there any possibility that the slides can be posted today so that they can be shared in that meeting?
Yes,
Well,
well, at least we will send them to the people who will do the posting. I can't
No,
vouch for past that.
it can be on the website within minutes.
That's what
Yeah.
I was hoping. Yeah, thank you.
Perfect.
Okay, great. Thanks, everyone. Join the Roman Science Collaboration. Keep participating. Propose early and often to our upcoming calls.